Next, we move on to transpose of a matrix. First, we'll go for the definition. If A equal to Aij be an m by n matrix, then the matrix obtained by interchanging rows and columns of A is called transpose of A. The transpose of matrix A is denoted by A dash or AT. In other words, if A equal to Aij m by n, then A dash equal to Aji n by m. Okay, I'll start explaining from the beginning. This is the standard form of representing a matrix. A equal to Aij, be an m by n. The order is m by n. And what we do here is we are interchanging rows and columns. When we interchange rows and columns of a matrix, you call transpose of that matrix. Okay, so how do you denote it by? You denote it by A dash or A raised to T. In other words, if A equal to Aij, this is a normal matrix, okay. Then A dash equal to Aji n by m. What will happen when you transpose? Order will change, and if it is that is element of A21 will get interchanged to A12. Clear? Let's see. When we go for an example, we'll understand well. Okay. So here's an example. Here's a matrix A, 3, 5, root 3, 1, 0, minus 1 by 3. Okay. So what is the definition? Rows and columns get interchanged. Now this row will become column. So how will you write? 3, 5. Again, this row will become a column, root 3, 1. Again, this one, that is 0 minus 1 by 3. Is it clear? And it is denoted by A dash. Got it? Did you notice what was the order here? 3 by 2. The order got interchanged, right? 2 by 3. Clear? Okay. Properties of transpose of matrices. So what all property we have? A dash whole dash is A. That is, if A transpose is there, if we again take the transpose, what will happen? We will get back the original matrix. K A dash equal to K A dash, where K is any constant. We have learned the scalar value. Okay, so A plus B whole dash is equal to A dash plus B dash. You should remember this is all properties. Why? Because later we'll be using it. Okay, so AB whole dash is equal to B dash A dash. Make a note, it is AB whole dash equal to B dash A dash. Okay, this is all important, you have to remember. Okay, next, symmetric and skew symmetric matrix. See, as we learned transpose, right? Now from transpose only we'll go for symmetric, and then we'll go for skew symmetric matrices also. So let's see. Square matrix A equal to Aij is said to be symmetric if A dash equal to A. That is, Aij equal to Aji for all possible values of I and j. When we say symmetric matrix, that the matrix should be a square matrix. Okay. 2 by 2, 1 by 1, 2 by 2, 3 by 3. In this form the order should be. Clear? Okay. So here we have an example. A equal to, see, this is an example. Okay. Now what they're saying is a symmetric matrix. Did you notice this one? What is, see, Aij? If it is A12, it should be equal to A21. Just see the element of A12. What it is? 2, and it's equal to A21. We'll go for A13. It should be equal to A31. Then diagonal elements, there won't be any changes, okay, when it is symmetric. Okay, then A23, A32. Is it clear? Okay. Symmetric means, see, if you fold the matrix from here, see, it becomes symmetric, right? This 2 will come over this 2, 3 over this one, -1 over this -1. So this is a symmetric matrix, so you can say A dash is equal to A. Clear? Okay, even if you interchange the rows and columns, you'll get same matrix. So A dash is equal to A. So symmetric matrix means what it is? A dash is equal to A. Next, definition for skew symmetric matrix. A square matrix A equal to Aij is said to be skew symmetric matrix if A dash equal to negative A dash equal to negative A. That is Aji equal to negative Ij for all possible values of I and j. Now if you put I equal to j, we have Aii equal to minus Aii. Therefore, to Aii equal to 0 or Aii equal to 0 for all i's. That is, if you have a skew symmetric matrix, it is saying that your diagonal elements will be 0. Okay, in your skew symmetric, your diagonal elements will be 0. And if this is negative 1, what will happen? This will be 1. And if this is 3, negative 3. And if it is 2, this will be negative 2. Now when we interchange rows and columns, what will happen when you take the transpose? So this 1 will come over here and negative 1 over here. So all rows and columns get interchanged. When rows and columns get interchanged, what happened? Here we had negative 1, it became positive, and the positive 1 became negative. So what happened? Our matrix A became negative. So here it is said that A dash equal to minus A. So when it is a skew symmetric matrix, that is transpose of that matrix is equal to negative of that matrix. When it is symmetric, transpose of that matrix is equal to the same matrix, that is A dash equal to A. In case of skew symmetric matrix, A dash equal to negative A, where not only that, first it should be a square matrix and your diagonal elements in skew symmetric matrix will be 0. Is it clear? So next we have theorem based on your transpose of matrix. For any square matrix A with real number entries, A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. That is, what is supposed to prove here? A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. When it is symmetric matrix, what is supposed to prove? What does a symmetric matrix says in definition? A dash equal to A, right? Okay, so that means what you have to take? Transpose of this whole thing. Okay. Okay, fine. Let's move. So let B is equal to proof. Let B is equal to A plus A dash. Then, so what? As I said, what you will be taking? Whole transpose, right? Why? Because we know according to definition A dash equal to A. So that means A plus A dash whole dash. Okay. So A plus A dash whole dash. Okay. You remember the property of your matrix, property of transpose of matrix, A plus B whole dash equal to A dash plus B dash. So, A dash plus A dash whole dash. Okay. A dash equal to A. Again, property of transpose. A dash whole dash is nothing, A itself. Did we get back the same thing, A plus A dash? Yes. So, we can say what A plus A dash is symmetric. Okay, which is equal to B. Next, C is equal to A minus A dash. We know that when it is skew symmetric, according to definition, A dash equal to negative A, right? So what you will do in this case, you will be taking the whole dash of this and you should get negative of this one. Okay, we'll see how it is. So let C is equal to A minus A dash. So we are taking the transpose of C. That means A minus A dash whole dash equal to A dash minus A dash whole dash. Is it clear? A minus B whole dash is A dash B dash. So Okay, next, so a dash minus a dash whole dash is nothing, a. So we got it, right? Your next step will be what you know, minus a plus a dash. Okay, only that step they have skipped, so it's not like for you to get confused or something. So here you take minus common. When you take minus common, within bracket what will be left? A minus a dash equal to minus c. So we got it right. So we can say that a minus a dash is a skew symmetric matrix. Next theorem. So any square matrix can be expressed as sum of a symmetric and skew symmetric. Okay, here a is equal to half a plus a dash plus half a minus a dash. When your proof begins directly with this, did you understand anything? No, just let us bring some clarity. We have a matrix A. Okay, let there be a matrix A. Okay, fine. Next we can we write half a plus half a? Yes? Yeah, you agree with that because half a plus half a is nothing, a. Okay, so here we got it. Next step, you add a dash and subtract a dash. Okay, plus a minus a dash. Clear? Okay, so next time we can write half a plus a dash plus half a minus a dash. So I guess you haven't got an idea like how we have this step. What we are supposed to prove that any square matrix can be expressed as sum of symmetric and skew symmetric matrix. Sum of symmetric and skew symmetric matrix. Clear? So same way a plus a dash is symmetric, that is proved here. We have proved in the previous theorem, and a minus a dash is the skew symmetric matrix. So when you sum up, you get a square matrix. Is it clear? Okay, so here we are done with this theorem. As we have proved this, I am not repeating it, okay? Here we have an example. So express matrix B, 2 minus 2 minus 4 minus 1 3 4 1 minus 2 minus 3 as sum of symmetric and skew symmetric matrix. What did we learn from the previous theorem? That is, sum of a symmetric and skew symmetric matrix is a what? We'll get a square matrix. So when we sum, so this matrix can be expressed as a sum of symmetric and skew symmetric matrix, right? So from theorem we already know this form, right? So first what you'll prove, a plus a dash. Since here we have b, so b plus b dash we'll find first, right? So here we have b matrix, we'll find the transpose of b. So transpose of b we got over here. Just we take it as b p. Okay, p equal to half p plus b dash equal to half. After adding b and b dash we get, that is 2 plus 2 4 minus 1 minus 2 minus 3. So we know after adding we get this. So what half is multiplied to each of the elements in the matrix. So this half is nothing, scalar value which you multiply inside the matrix to all the elements. So when you solve it, 4 by 2 2 minus 3 by 2. So here we get the answer for half b plus b dash. Okay, next. So what is done here? We are finding the transpose of this one. Why transpose of this one is found? Because you remember in the theorem when we worked out, we found the transpose of a plus a dash. Yes, why? To check whether when we take transpose, we are getting the same matrix. Only if you get the same matrix, then only what that matrix is symmetric. Okay, so when the transpose is taken, yes, we get the same matrix P. P is nothing, this matrix. Okay. Next, Q. Half B minus B dash. That is to find, to show that it is a skew symmetric matrix. So we find the difference of B minus B dash. So after finding difference of B minus B dash, we multiply each and every element of the matrix with half. So these are the value. First, for skew symmetric, we know that diagonal elements are 0. Yes, this is okay. Now what we are supposed to do, we have to transpose. Okay, when we transpose, what happened? See, this is positive, but in the as Q, what it was negative, and this half became positive, half became negative. So see, all sign has, what is a twist over here? The sign gets changed when you change the rows and columns, right? Positive becomes negative, so that is negative Q, right? So as according to the skew symmetric definition, we know that A dash equal to negative A, that is Q dash equal to negative Q. Okay, so that is Q is equal to half B minus B dash is a skew symmetric matrix. So when you add P plus Q, what you're getting? You're getting the matrix B itself once again. So B is represented as sum of symmetric and skew symmetric matrix. Okay, next. One more example. If A equal to minus 2, 4, 5, B equal to 1, 3, minus 6, verify that AB whole dash equal to B dash A dash. This is nothing, we are verifying the property of transpose of matrix. Okay, since here the order is how many rows, how many columns? 3 rows and 1 column. In this case, 1 row and 3 columns. Okay, so this AB is defined here, and we'll have a resultant matrix of 3 by 3. Okay, so we'll find the AB. So when we find, multiply minus 2 into 1, then minus 2 into 3, then minus 2 into minus 6. Okay, the next second row, first column, 4, then 12, then minus 24, 5, then 15, minus 30. Okay, easy, right? As we have done in the previous exercise, multiplication. Okay, now next, when you find the whole dash of AB, what you will get? Minus 2, then minus 6, 12, then 4, 12, negative 24, then 5, 15, and negative 30. Just make a note, your diagonal elements stay as it is. See, if you want, you can do it directly in this way. These elements are getting changed. This and this gets interchanged when your matrix is, when you're transposing it, and this gets interchanged. Okay. Next, this is our LHS. Now RHS, B dash, A dash. So we find the transpose of A and B. So this is transpose of A and B. When you multiply this transpose B dash, A dash, you get minus 2, 4, 5, minus 6, 12, 15, 12, minus 24, minus 30. Okay, so you get this is equal to what? AB whole dash. So here our property is verified. So here we have exercise. This is 5 half negative 1. When you transpose, what will happen? Row will become column, column will become row. So 5 half minus 1. So this is a transpose. Here it will, here minus 1, then here 2. See, we will take the transpose. Okay, transpose is easy, not so tough. Second question, here you have to verify what a plus b whole dash equal to a dash b dash. So here we have two matrices, so when we add, our order is same, so no problem. According to rule, we have same order in both the matrix, so we can add. So we'll be adding first. Okay, so when we add, see, this is what the resultant matrix we got. After adding, we find the transpose. So this is our transpose. Okay, see, rows and columns get interchanged. Okay, so this is our LHS. Now we'll find RHS. Okay, RHS, what is RHS? A dash plus B dash. Okay, so here we have A dash plus B dash. So this is the transpose of A and this is the transpose of B. So sum of the both A transpose and B transpose, we got this. So this is equal to what? LHS. So can we say our property is verified? Yes. Okay, next. This is a second sub question based on the same matrix in the previous sub question. So here we have to verify what A minus B whole dash equal to A dash minus B dash. So again we take the LHS. What is LHS? A minus B whole dash. So first we'll solve what? A minus B, difference of A and B. Okay, so when you find difference of A and B, this is our resultant matrix. Okay, so later we'll take the transpose. So here we're taking the transpose, we got the transpose also. Rows and columns get interchanged. Next are RHS. What is RHS? A dash minus B dash. Okay, so first the transpose of A, this is a transpose of A, and this matrix is transpose of B. So finding the difference, what did we get? Same as what you got for A minus B whole dash. So again here LHS is equal to RHS. So again this property of a transpose is also verified. Next fifth question, for matrices A and B, verify AB whole dash equal to B dash A dash. Again this is a property of our transpose. So here we have two matrix. So what, first we'll find the LHS AB whole dash. Before finding A whole dash, we'll first find AB, that is product of A and B. For finding the product, what do we check? The order, right? CR first we check, right? Whether CR is equal, that is column and row, column of first matrix and row of second matrix are equal. Okay, it's equal, so AB is defined, so we multiply. And can anyone see what will be the resultant matrix? Yes, the order 3. So here we got the resultant matrix minus 1, 2, 1, 4, minus 8, minus 4, minus 3, 6, 3. So we found the product of AB, and here we have to find the AB transpose, that is AB dash. So after transposing, this is our resultant matrix, that is AB whole dash matrix. Next, our RHS is what? B dash A dash. So you have to find the first transpose of B dash as well as A dash. So this is a B dash and this is a A dash. So this is the transpose. So after finding the product, this is a resultant matrix. So this is equal to what? LHS. Just check. Yes, same thing. So again here a property of transpose is verified. Next, here we have another question. If A equal to cos alpha sin alpha minus sin alpha cos alpha. This cos alpha sin alpha, it's like behind, it's found in every exercise. Then verify that A dash A equal to I. Solution. So first we write the given, then find the transpose of A because we need it, right? Then find the product. Okay, so this is a transpose. When you find the product, what do you get? Cos alpha sin alpha minus sin alpha cos alpha. Second row, first column. So sin alpha cos alpha minus sin alpha. sin alpha, sin alpha, cos alpha, cos alpha. So cos alpha, cos square alpha, minus minus positive, so sin square alpha plus sin square alpha. So cos alpha sin alpha minus sin alpha cos alpha, cancel, 0. This sin alpha cos alpha, so plus minus minus we have, so cos alpha minus, minus comes over here, so here we have cos alpha sin alpha, so it's cancelled, so we have 0 here. Sin square alpha plus cos square alpha, and we know that sin square plus cos square is equal to 1. Okay, so 1 0 0 1 proved, right? Equal to RHS, I, identity matrix. So hence verified. Next question, show that matrix A is symmetric matrix. How it will be symmetric? Simple, find the transpose. If transpose is same as it is A, then it is a symmetric matrix. Yes, when we find the transpose, it is same as it is. So A is symmetric.